Okay, recording is in progress. Is that? Okay, so what I want to do today is just give a general overview of this section as I understand it and as I was reading it, because I feel like I got a little bit of different perspectives than necessarily just Professor Lee's perspective. Because I have studied in grad school, I've studied some dynamical systems that didn't necessarily touch on this section so much, but I've also studied math modeling, and math modeling made a lot of use of these types of differential equations. And so I'm very comfortable myself working these kinds of problems. I almost didn't recognize it at first because in math modeling, typically you'll have t as your variable because you're always talking about time in the real world in all practical cases. And so I almost missed the connection between what this chapter is talking about and the experience that I had. But yes, so this chapter is specific, or this section is specifically talking about homogeneous linear equations that have exclusively constant coefficients. So all of these a sub I of x are constant functions. In general, and Professor Lee mentioned this in his lecture, in general, e to the mx will always be a solution to something like this, where m is a specific value. So you'll always have some solution of this form. But in particular, where m is a root satisfying the auxiliary equation, sorry if I say that weird, where the auxiliary equation is found by changing each of these ith derivative of y's into m raised to the I, and considering this as a polynomial instead of as a differential equation. And this is wildly useful. Oh my goodness, I could list applications of this, from tracking disease to tracking populations to all sorts of things. This is widely applicable. This is very common in the real world. The problem with this is that this auxiliary equation might not be nice. Even though it's constant coefficients, they're even constant real coefficients, right? That's honestly narrowing it down a lot, but it won't always have very nice roots. And so we have to develop a couple of tools for how to deal with when these roots are repeated or when they're complex, right? So I have written here, this like second half of this page is some of the most useful basic knowledge that a person can have going into solving equations like this in general, right? Any problem that falls into a homogeneous linear differential equation that has constant coefficients, you can reference these two steps and they will guide you, right? So any real root that has multiplicity k, that is, it shows up that many times, or m, or x minus m is a root raised to the kth, right? Generates k linearly independent solutions where the first one has the form e to the mx, but we can't just repeat that, otherwise they're not linearly independent. And so it is mathematically consistent and very convenient for us that this works, that we can say, okay, well, just multiply an x out front every time you need an additional one of that form. So if you have a final solution that has x squared e to the mx in it, that implies subtly that there had to have been two more before it. Otherwise, you wouldn't have used this one, right? So when we're dealing with real roots, they're very easily approachable. You just find the roots of this polynomial auxiliary equation, and you write them in e to the mx, repeating with multiples of x as necessary. Okay. For complex roots, however, they're a lot more complicated. And Professor Lee goes into good detail with this in his video. It turns out the specific, we have what I have, by applying the homogeneous corollary of theorem 4.1.7 from last week, we see that we can always find real solutions. He goes into really good detail about how that happens, starting from the complex solutions that you have and multiplying 1/2 times y1 plus 1/2 times y2, you get out, I believe, this one. And by multiplying, yeah, this one for sure. And by multiplying 1 over 2i times y1 minus 1 over 2i times y2, you get out this one. And we know theorem 4.1.7, so that you don't have to reference it necessarily, is just saying that linear combinations of solutions are solutions to a linear combination of the g of x on the other half of the equation, right? And so all of these that we're dealing with are homogeneous equations. And so the corollary that we had right after that was that every linear combination of solutions to a homogeneous system will also be a solution to that homogeneous system, because the linear combination of a bunch of zeros is 0. And so that's all we're using here. And Dr. Lee does go into good detail there. But complex roots have to come in conjugate pairs. So there's no way that we will ever not have plus or minus beta here, right? We always will consider them as the real part and the imaginary part. And use this, what is it, Euler's form, I believe, for expressing these numbers. And we can use that to get out real solutions. So this all, I don't know, I'm brushing over it a little fast, but the lecture video went into good detail on it. And so I'm not too worried about this. As long as you know that these can be applied to as many repetitions as necessary, right? If you have an arbitrary value n for the degree of this, you might have 12 different roots, some of which are repeated, some of which are complex, right? But that shouldn't intimidate you. That should be easily enough approachable, aside from the fact that humans, as far as we're aware at this point, are not very good at solving polynomials, factoring polynomials. It's one of the most difficult areas of mathematics, while being deceptively simple, because very low level, very low degree polynomials are simple to solve. Well, 5th degree is actually pretty complicated, but there's a formula that you just plug it in and you follow it and it hands you back your answer. But above 5th degree, there's no formula. It's just a matter of, can you find some way to reduce this? And as a whole, mathematics hasn't gotten to a place where we're very skilled at that yet. And so that's really the difficult part of working with these in the real world. In this class, there's no way we would ever hand you something of degree 5 or higher. Like, oh Lord, that'd be cruel. You will almost definitely see some 3rd degree problems. But primarily you'll just be working in 2nd degree, and you can always use the quadratic formula for 2nd degree, and so it shouldn't ever be an issue. Of course, you know, all the usual calculus recommendations. Be careful when you're factoring so that you aren't dropping signs and things like that, because that'll spit you out wrong answers. Okay, fine. I wanted to mention right before I get into that a little more, that here intuitively, if a conjugate pair of roots is repeated, like you have, you know, you'll always have m or x minus m1 times x minus m2. Those will always come in pairs, but you could always have x minus m1 to the 3rd times x minus m2 to the third, that each of those comes in a pair, but you can have repeated complex roots. Of course, if they are repeated, we intuitively, just similarly to the way that we did these above, we'll just multiply an x in front of their solution, each solution, so that it is representing the same root, but is also linearly independent from previous solutions. So it's all very intuitive, this section. But yes, a fundamental set of solutions to a homogeneous linear differential equation with constant coefficients is found by just making a list of all of the solutions that are generated by the roots, as listed here, right? If you have a root with multiplicity 5, then you'll have y1, y2, y3, y4, y5 from this list, all as your, c1 times y1 plus c2 times y2, etc. And if you have a complex root on top of that, you'll just have a plus c6 times this, plus c7 times this, right? So your general solutions will be very straightforward for problems of this type. Hence, solutions of this type of differential equation come down to only how are your factoring skills and how comfortable are you applying them over the complexes. I think a lot of people maybe at this point have never dealt with complex numbers in any real way. And so factoring into complex numbers can be really uncomfortable at first. Okay, example 1. Find the general solution of this second order linear differential equation. Okay, we have, oh, that was already popped up. Example 1. We have 3y double prime plus 2y prime minus y equals 0. Okay, where do we begin? First of all, this has constant coefficients. It is homogeneous. Those are both really quick to check just by sight.
Yeah, so it's, you do the equation, the
Mm-hmm.
pream,
You want to get the auxiliary equation.
yeah.
And that is what here?
So it's 3m to the 2, I don't know.
Mm-hmm.
Yeah. Minus 2m minus 1. Oh, plus 2m.
Minus 1, yes.
Minus 1, yeah.
Okay, so factoring this. Of course, like I've mentioned before, this is an online class. You guys have all of your tools at your disposal. So you could just plug this in somewhere. For myself, I know a nice trick for factoring non, what are they called? Mono, whatever, non-mono, i.e. having not a 1 as the first coefficient, binomial things, that a student taught me last year, which is so cool. You magically, this is not magic. I've proven that this works before I go on to use it myself, but it's really cool. You take this 3 and multiply it to the last one instead. Consider how you would factor 2m minus 3 here. Consider how you would factor this m squared plus 2m minus 3. Monic. It's just called monic. That's the word. Okay, with this, you need ab to equal -3 and a plus b to equal +2. Of course, I'm looking at -3. Oh, +3 minus 1. Here we go. And -3. Said it backward again. And +3 and -1 here. So this polynomial would factor into m plus 3, m minus 1. But what you can do, because we multiplied our a over into our c so that a is just 1, the way to reverse that process is to one of these two, one of the pieces of the resulting factored object will still be divisible by a. And so multiply it over to the corresponding m, and you suddenly have m plus 1 times 3m minus 1. And this works. I've proven it mathematically. It is very intriguing to me. I never was taught this in school. But this is then the correct factoring of the original polynomial. So this is the undoing of the magical step, right? So the factor of this, factored version, is 3m minus 1. And if you are a fan of working things out sort of abstractly, I highly recommend doing an example like this where it's ax squared plus bx minus or plus c, right? So that you can really see why this actually works. Of course, like I said, it's an online class. You don't have to hone your factoring skills or practice them in any way technically, but it saves a lot of time, basically. So that you can get your roots out of this immediately, right? You get m equal to -1 or m equal to positive 1/3.
Yep.
Okay, so we have the roots. Now what?
Now our solution is C1 multiplied exponential x2 divided by 3. Yeah, I don't know.
All right.
Plus C2 exponential of minus x.
Correct. Yes. Y equal to this is the general solution.
Yep.
Yep. To this DE. Yeah. Beautiful. So these problems should be extremely accessible in general. All right, find the general solution of the higher order linear differential equation.
It was the same thing.
We do essentially all of the same steps. It's a matter of finding your roots and knowing how to approach them. So y third derivative plus 3y second derivative plus 3y first derivative plus 1 equals 0. This is m cubed plus 3m squared plus 3m plus 1 equals 0. So where do we start with this? I think the biggest difficulty with problems that are higher order is just figuring out how to factor them.
Yeah, you have to try it. So I try it, and I came to m plus 1 cubed equals 0.
What was that?
M plus 1 cubed. Everything is cubed. So I don't know if that's right.
Do you mind typing that in the chat?
Okay, sorry.
Yeah, no worries. I wish that I could see what you all were writing ever. Dang. That's one of the really valuable things. Oh, I see. M plus 1 cubed equals 0. Oh, yes. Yes. Okay, you were just skipping steps. I see.
I just try it.
I was trying to listen for like a number, and that just isn't what that was.
Okay. I just tried n plus 1, and I was trying other stuff, and then I came to that one. So
exactly. Yes. My first impression of this was that you notice all the coefficients are paired with an odd and an even power of m, which is to say that -1 is a really good guess, right? If you plug -1 in here, you'll have a -3 and a +3 cancel out. You'll have a -1 and a +1 cancel out. And so I took out an m plus 1 immediately and then was factoring the rest of this. And I was like, oh God, that's just coming out to m plus 1 times m plus 1. Oh God, this is just m plus 1 cubed.
yeah.
So going the long way around to this, but arriving at this answer. Exactly. So then we have this repeated root. This gives us m, well, I'm going to say m1, m2, m3, all equal to -1.
Yeah.
Okay, so then the general solution looks like what?
C1 multiplied by explanation of minus x plus
Mm-hmm.
C2 multiplied by x multiplied by explanation of minus x. I don't
Mm-hmm.
know if I have to, so the minus also, no, I don't think it goes. So, and then C3, because it can be on on the C's. So, yeah.
Yeah, exactly. Mm-hmm.
C3
Precisely.
multiplied by x squared,
Mm-hmm.
multiplied by explanation of minus x.
Perfect. Yep, y equal to this is the general solution. Awesome. Yeah, this section is not terribly difficult to grasp as long as you essentially have seen this general form. As long as you know that each time you're multiplying by these x's to make sure that these are all linearly independent solutions. And we had sort of touched on that last week, hadn't we? That uh, by multiplying a variable times a solution, you immediately bring it out of being linearly dependent. There's no way to multiply a some number of times by a constant and get out ax. So
Yeah.
this is just a beautiful, intuitive section, I think. All right, solve the initial value problem. Y double prime plus 16y equals 0.
Okay, so you do the general, so is the auxiliary. So it's m squared plus 16m equals 0.
So be careful. Just
And
16.
the
Because
roots, I think
exactly, it'll be 16m raised to the 0,
yeah,
which will just be 1.
yeah.
That's a mistake a lot of people make when they're just starting this sort of form. So I wanted to point it out.
Okay.
But yes, m squared plus 16 equals 0. Okay.
And then through Bhaskara, I solved for the roots are 0 and minus 16, but I can be wrong. I don't know.
I don't think that I get that, because if you plug in 0, then you'll have 0 plus 16 equals 0. And minus 16 will come out with some very large number.
Oh, I know what I did. Okay. So
Hi,
do you
Thomas.
remember about the m to the 0? I did that. So I did
Right. Yes,
m to the 1.
exactly.
Yeah.
So be careful
Okay.
that this is m squared plus 16 equals 0.
So
then,
then you only have one root.
oh, that makes a lot more sense. Of course, 0 and negative 16 would be a solution. That negative? Yeah, yep.
Okay,
That would
so
be the solution if this had not canceled.
yeah, so your root is what is it? Not real. I forgot the name of that.
Exactly. We'll have
Yeah,
complex roots in this problem.
yeah,
Because
complex.
this is, you can think of this as a difference of squares, right? This is m squared minus negative 16.
Okay.
This is equal to 0, right? So when we talk about factoring this into a difference of squares, we have m plus something, m minus something, but what that something is the square root of negative 16. The square root of negative 16 happens to be 4i.
Yeah.
So m plus 4i times m minus 4i.
Okay.
Yes, double checking that I'm doing my math right. I mixed up at some point one of the examples that I've included here. I think example 4. That I was doing this sort of factoring and it wasn't the correct, like in my own scratch work.
Yeah,
Came back and was like, oh, that's why that didn't make sense. Right. Okay, so this is the factored form. These are the two roots of this
okay.
polynomial.
So then you have for your solution. So why? Because it's complex. So you have exponential to the alpha, but alpha is actually 0.
Uh-huh.
So you
So
have
e to the 0
only
x.
the sine and the cosine. So you have I don't know how to do. So it's c1 multiplied by cosine of 4x plus c2 multiplied by sine of 4x, I think.
I'm going to write this out, e to the 0 times x,
Oh,
just
okay,
for
okay.
complete clarity, but yes, that should be correct. And we can double check that here. Here, right? That we come out with the real solutions, and we can totally justifiably, even in your problem sets, jump straight here from recognizing that you have complex roots. You have complex roots, alpha plus or minus beta I, and you can immediately say our solutions have this form. Okay. So this is a thorough justification. So this is y equal to this, i.e. y equal to c1 cosine of 4x plus c2 sine 4x. How are you doing today, Tom?
Hey, I'm good. Sorry, there was a meeting that I couldn't get out of at work, so I had to miss the
there's
first half of
really
this.
no problem. Yeah. It's mostly really intuitive stuff. Anyway, I want to make sure that you guys see some sort of characteristic examples, but especially example 1, what we had, just a matter of factoring. I wanted to show off a cool factoring trick that I know that I have proven. It works. It feels like magic, but it works. And it's just a very straightforward solution. Okay. And the second example, just a matter of making sure that you know how to approach repeated roots. So it should be very straightforward, the first couple examples. So you haven't missed too much.
And I followed from the lecture how to do those repeated root problems, but I don't really feel like I understand why what I'm doing is working.
Aha. So if you look at, so I have this first page, the second half of this first page is dedicated to sort of describing exactly what we're doing. It doesn't necessarily go into a lot of detail about why that works, but what we know is that when you multiply a solution by x, that is inherently linearly independent from the thing that you had to start with. Because there is no way, right? Linear dependence requires or at least of two things, requires that one be a multiple of the other, a constant multiple. And so this cannot be, and we've sort of relied on this a lot in calculus as well when we're talking about like separation of, what am I trying to think? I was thinking separation of variables. That's not what, partial differential, God damn it, partial fractions. That's what I'm trying to think of. Damn, I am terrible with words. Okay. But when we're talking about partial fractions, we make this assumption, right? When we're talking about solving the system of equations that we come out with, this a plus b has to sum to 0 because that's the constant involved, and a minus b has to sum to 5 because that's the number of x's involved, and those sorts of things. In the same way, we can always cluster these by the power of variable out front. They will never be linearly dependent as long as each of them is identical, but with a different power of variable out front. So this is just sort of the the shortcut to your answer is to say that this works and is very easy. And so this is what we do. There are absolutely other ways to find solutions. There are other ways to write solutions, but this one is immediately straightforward and reachable by an algorithm. And so this is by far the preferred method.
Gotcha. And Julia, unless you have a specific question, I was hoping, is there a way we could go through like the most simple root problem and not skip any of the steps in terms of just plugging what it gives you into that e to the mx formula? Like
Oh, yes.
getting to that e to the mx, if that makes sense.
Okay, getting to e to the mx sort of is, yeah. Let's see. So this tells us, if you don't mind me jumping in sort of halfway through this problem, this is example 3. We've put it into its auxiliary equation and then double checked to completely point out this will trip people up. This y double prime plus 16y equals 0, it feels like it should be m squared plus 16m, but that is not the case. A single value of y is the 0th derivative, so it goes to m raised to the 0, so the m disappears. So just pointing that out. This then, we just want to factor whatever we get after that point. In this case, this is a difference of squares where the second square is complex, right? Root. The second root is complex. And so we come out with this complex conjugate pair of roots, which of course, based on this slide, we're in piece 2 of this, right? We know that what this spits out is we have alpha is equal to 0 for both of these, and beta is equal to 4, plus or minus 4, right? So y1 and y2 are equal to e to the mx. So this is e to the alpha plus or minus beta I x.
Right. So right there is the part that I am missing some like fundamental understanding of, in the sense that I don't get why, once we have those roots, imaginary or otherwise, we are allowed to plug them into that e to the alpha plus or minus beta I x formula in order to get our solution.
Sort of coming back to, I am disappointed that I don't have better words to explain it exactly, except that it has been proven that this is always a solution. Regardless of what that root looks like, you will have a solution of the form e to the mx. That will always satisfy this equation, this original differential equation. And Professor Lee, if you've watched the lecture video, he goes into, I think, okay detail. It might be worth rewatching that piece of the video to see, because he showed the mathematics on the slide, I remember, of plugging that in and simplifying it. And it's kind of ugly mathematics, but it works. It will always work.
Okay, was this the simplification with the
auxiliary equation to begin with?
Sorry, was that what you're referring to, the simplification where he has like the e to the something I term equals like x sine of something plus x cosine of something, or something similar to that?
I think it was before then. It was before then, because he did do this taking it from this Euler form where it's just e to the complex number times x, and writing this number in cosine plus sine things form. And that's how we arrived at these real solutions. That also is really well hashed out in the lecture video. But yeah. I think it's a lot earlier when he's first introducing this auxiliary equation. He shows the mathematics behind, you start with your differential equation, and it's true, it's a proven mathematical truth, just like many other, like the fundamental theorem of calculus was once just a theorem that somebody proved. In a similar way, this is a true fact that this will always be a solution. So, okay, it'll be a solution for some m. And then the question becomes, okay, but for what m? And so what they did was they plugged e to the mx in for all of these y's, they took their derivatives appropriately, and they figured out, okay, what can I simplify this down to? How can I just titrate out exactly what I need from this? And what that simplifies to is this auxiliary equation. So any m that satisfies this equation corresponds with an e to the mx that satisfies this differential equation.
Gotcha. Yeah, I think it will be helpful for me to go back and rewatch that part of the lecture.
Yes. For myself, having seen that proof before already, I didn't pay a lot of attention. I recognized and appreciated that the math was on the slide, and I left it at that, like, yep, somebody proved it. Cool. Moved on. Like, but it is there. He does show the steps in between, and so I recommend watching that
Okay.
bit of it. It's a little complicated. He doesn't like read it out loud or anything, but if you pause the video and work through those steps yourself, I think that it should be straightforward enough.
Sure.
Yeah. But the conclusion of that is that it has been proven that any m satisfying this corresponds to e to the mx that satisfies this. So if we solve this, then the implication is that we have a solution to this.
Got it.
And the beautiful and tricky part of that is that e to the mx is sometimes not at all nice and sometimes not enough, right? If it is a complex root, then e to the mx is not a real solution. It's a complex solution, which is valuable in its own special way, but not really in a real world sort of way.
So lingering on that for a minute, a few of these recitations ago, I asked you if we were considering imaginary solutions in this class.
Yes.
And I'm now worried that I approached the first problem set incorrectly because I just argued the solutions here are
no.
imaginary,
Okay.
therefore no solution.
Exactly. So on problem set 1, we had not talked about any of this, first of all. So we won't, as far as I know, I'm pretty sure that the grader is not taking that into consideration, that we're only considering real solutions because we've only talked about real solutions. In this case, technically, there is one in particular very easy way to turn complex solutions of this type into real solutions. And so we give you the explicit 1/2 times y1 plus 1/2 times y2 gives you a cosine thing, and 1/2i y1 minus 1/2i y2 gives you a sine thing. And both of those will be real, always, period, done. But no, for the problems that were previous to this section, we definitely did not want to consider real or non-real solutions.
Got it.
And in this section, even, we won't accept non-real solutions as an answer, right? The whole issue here is that, okay, e to the mx, where m is complex, that's not nice to work with in any kind of real world situation. But we can use the theorem that we learned at the end of last week to come out with these real solutions that are just as good. And that's the other thing. The problem set was last week, but we didn't learn this theorem until the end of last week. So there's no real reason that we should have expected that of you guys. So in short, don't worry about it. The brief form is, don't worry about the complex solutions. I stand by what I said, whatever, 2 weeks ago.
and it would be true to say that we can only ever navigate out of that situation of complex back into real solutions when they are of specifically this form, right?
I want to say, like, maybe technically no, but certainly this is the only scenario where we would expect you to.
Okay.
Yeah. Maybe technically you can do it for other things, but unless we specifically give you guys tools to be able to do that, don't expect us to require it of you. Yeah, many, many, many times there will be complete justification to say this thing doesn't work because the answer is complex. But I wonder, that does raise a good question, because anything that can be written as e to the complex number times x can be written as this e to the alpha x cosine of beta x plus e to the alpha x I sine blah, 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 blah. Or I misread that anyway. But I think that's about right. But yes, it can be written in this other form with cosines and sines. And so anything that has this Euler form could be always translated into real solutions. But I think that, oh God, like if you had just a random polynomial natural log of a complex number, like, oh God, there's very little to be done about that.
And so up above in 1, where you have y1 equals e to the x something, y2 x e to the x, y3 x squared, etc. When we're looking at in 2, where how you get those back into real form, how does that change when you do have that y3 with the x squared term, that yk with the k minus 1 term, etc.?
Exactly. So intuitively, the reason that, sort of justifiably, the reason that we were doing this was so that we could keep these linearly independent of each other. Just because it works and it's easy, right? So that is the tool that we use. In the same way, if you have repeated complex roots, you can just multiply an x out front. You would have e to the alpha x cosine beta x plus e to the alpha x sine beta x plus x e to the alpha x cosine blah, 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 x e to the alpha x, etc. And I've got a couple examples looking at things like that.
Okay.
Which conveniently we're just reaching after this one. So, all good?
Yep.
Cool. This point 1 and point 2, I think are excellent resources, because any linear differential equation that falls into this category, you can just reference this half a page and know exactly where you need to take that general solution. You just look at, what are your roots? What's the multiplicity of each of these roots? Okay, done. So it becomes very, very straightforward, very algorithmic. Okay, example 4. Oh, please keep scrolling. Here we go. Two roots of a cubic auxiliary equation with real coefficients are m1 equal to -1/2 and m2 equal to 3 plus I. What is the corresponding homogeneous linear differential equation? And is your answer unique? So, example 4. We have m1 equal to -1/2. We have m2 equal to 3 plus I. This is a cubic auxiliary equation. So we know that the power, the maximum power here is 3. So we know that we have some kind of a m cubed plus b m squared plus c m plus d equals 0 was our original auxiliary equation. And if we know that two of the roots are m plus 1/2 here, and m minus 3 plus I. We know that these have to be some factors of this. Okay. What else do we know about this, given only the information that we've been given? There's at least one thing that definitely should be recognized here.
We need a pair.
Mm-hmm. So what is the root that they didn't give us?
3 minus I.
Mm-hmm. Exactly. Implied by the existence of this complex root is the existence of its conjugate as a root. And so we have m minus, this is the problem that I mixed up. I was doing an m plus 3i and m minus 3i, and oh geez, that's not correct. That's not correct, just in case you catch yourself doing that. 3 minus I. You always have m minus the root, and that root itself is the thing that's switching from plus to minus. Okay. So we know, based on the information that they gave us, we know that these are the roots of this polynomial, that these are the factors. Technically, we can have like a 5 out here. That's totally valid. Is that going to change anything though? Like technically, but only technically, because it's just a coefficient and it's equal to 0, right? So before you even started putting this into its auxiliary equation, assuming you were working the other way around, you may have noticed that every term of this differential equation is divisible by 5. So divide by 5 and get rid of it. So the only way for these to be different, the only way for your answer to this question to be distinct from someone else's answer is in this coefficient out front, this multiple that is affecting every term in this case, the auxiliary equation, but also then in the differential equation, right? If we scroll up
Should
a
we
little bit.
be expected to factor a cubic polynomial in order to find these roots?
So yes.
I don't know if I
You
am fresh on that.
have exactly. I have this, when it comes down to this, how are your factoring skills? How are they over the complexes? That you have the benefit of being in an online class. You can use calculators, you can use online resources. You have plenty of ways to get around needing to be quite as fresh with your factoring skills. It will take you more time, which is the only real cost to you. And so I recommend brushing up on that. I can link resources for very good sort of review of general factoring forms, because I, as an undergrad, was complete crap at factoring because I had skipped algebra 2 in high school. And so I just didn't have a lot of the tools that my classmates did. And so, oh God, factoring a cubic thing? Holy cow, there was no way. There was no way. My whole approach was like, you just, either you see it, I knew the like, for a quadratic, right? You have the a times b equal, like only for a monic quadratic polynomial was I very comfortable. Yes, aside from using the quadratic formula, I guess I could have done that, but wow, that's a little heavy-handed sometimes. But yes, when my peers would just be like, obviously that factors into m plus 2 times m minus 7. I was just like, okay. But I gained a lot better appreciation for it when I taught algebra for the first time. And I was reading their textbook like, oh my God, I was never shown these tips. Like, these are great. How do people, like, you have all of these tools that I just never had, that I had just ridiculous ways of compensating for at the time. But yes, so reviewing your algebra can have a huge, huge impact on how this all feels.
And in terms of resources, I was just imagining Khan Academy. Is there a
Oh God, PurpleMath is so good.
okay.
Highly recommend PurpleMath. As far as it used to be, they've grown essentially, is what I'm saying. Especially through COVID, they've grown their efforts. But they used to have just very good like algebra review. And now they have a lot more like algebra and geometry and trigonometry and basic calc. And so it's a very, very, very good resource. Highly recommend it. They have detailed explanations and work examples. It's essentially like a text document version of a recitation.
Awesome.
So I really appreciate it for myself and for my students. Sometimes I need to go back and remember how the hell do I complete the square? So yes, this incredibly useful. We were working this. Yes, and is your answer unique? The only way it could be different is this coefficient out front. And so essentially, yes. Ooh, looks like the recording has paused.
So you would take those roots from the auxiliary equation that we just found, and then you would plug them into our solution. If 5 with the auxiliary or the factored auxiliary equation, where would that end up in the solution?
So the thing is that it wouldn't end up in the solution because you totally would just divide it away on the other side.
Okay.
So that's the only thing. When you're talking about working these problems backward, there's no impact that that coefficient would have.
Gotcha.
Yeah. This is telling me, due to low bandwidth or local computer conditions, video is not currently available. Video will resume automatically when conditions improve. Okay. I trust you, computer. This means I can't see my own video. Okay. So, is my video changing for you all?
Your handwritten video is gone for me. I can see the screen that you're sharing. I don't know if it's updating. It's looking at example 4 for me.
Okay, if I scroll down here.
Yes, it's working.
Okay, cool. Well, that's great. This is a little bit more of a discussion example anyway. Okay, so suppose a homogeneous linear differential equation has this as one given solution. What is the minimal possible order of the corresponding differential equation? Assuming, of course, that they followed the rules that we were following and didn't just add random x's in for no reason. Technically, a person could do that, but that would be ridiculous.
Is it a 4th order differential equation?
So let's see.
I think it was
should be. What's that? Go ahead, Julia.
It's just I think because of the cosine and the 3 in the sine, it's for sure to a 2nd order. So you have something that has to go to complex, and then you have the e to the 3rd, so the exponential to the 3rd x, and you have the other one that is x. I don't know. It's just because of the x to the squared, the x squared. I would think. I don't know.
That's all really, for one thing, that's accurate. For another thing, that's really good intuition.
Okay.
Seeing this cosine and sine, you immediately know that you have a complex conjugate pair. So you immediately know you have at least two as your power, right? You also have two other terms, right? So you have at least four, okay, but we can say even more about this, right? Because we have x's in front of some of these, assuming that they're following the same guidelines for a solution that we would, right? They would have had some c1 e to the x cosine x plus c2 e to the x sine x, but we have 3x e to the x sine x. That means that that was a repeated root.
Oh, okay. So you have 3 there. Oh.
Exactly. So we have an e to the x cosine x, an e to the x sine x, an x e to the x cosine x, and an x e to the x sine x. So you have at least four just made up of complex roots.
Okay.
Does that make sense? Using that x to sort of fill in what isn't, because the thing that's happened here, I've given you specific constants as your coefficients for this solution. That is to say, some of them may have been 0 and have dropped out.
Okay.
So
So
the
it's
way
just
that we have this written, I'm not sure if the WebAssign will give you a question like this. In my own math modeling class, we were given questions like this, certainly.
So I am kind of lost. So it's a 6th order then?
At least.
Okay.
There's even one more. Yeah, this one is way. There's no way that we would ever ask you to solve something this complicated. But looking at the solution, looking at the general solution or a specific solution like this, you can say specific things about the original differential equation by working this backward.
Why is not a 7th order then?
Aha!
Just
Exactly.
because
Why
if
isn't
you
it?
have
Or perhaps is it?
Yeah, because if you have a cosine with just a constant, you already have a sine, but the constant drop out, so you don't have it there. And then you have the 3x for a sine that has another cosine, so you have 4 roots there.
Yep.
And then for the rest of the equation, you have also, since you have the x squared, you know that you have the one without the x, the one with the x, and the one with the x squared. So you have a 7. I don't know.
So this is exactly, that is perfect reasoning.
Okay.
The answer here is the minimal possible order, the minimum possible order that this could be is 7th order.
Okay.
For exactly that reason.
Okay. Awesome.
Hey, Iris, do you want to say hi to my class? Hey, see ya. Okay. Toddler came in and left again. But yes, so I have given example of a differential equation that might have this as a solution. I myself did not write one out, but I would only, if I were ever asking this of you, I would only ever expect you to write it in the way that I did that previous one, just as the factored chunks. It would just be recognizing that one of the roots is 1 plus I, and so there's the implied 1 minus I.
Okay.
That is repeated at least twice. And then the other root would be positive 3, and that's repeated at least 3 times. So you would have m minus 1 plus or minus I all raised to the 2 times m minus 3 raised to the 3. And that would be how I would write it. So I wouldn't expect you to expand that or anything.
Can you write that down on the comment?
So I don't know if, oh yeah, I can write
Yeah.
this in the chat here. I type it on the document. I don't think I can type it easily enough. Anyway, in the chat, let's see. We would have m minus parentheses 1 plus or minus I. That's going to look really strange in single line format, but that's fine.
Thank you.
M minus this thing, parentheses raised to the 2 times m minus 3 c's raised to the 3. There. This would be the briefest possible way to write, oh, well, this isn't the differential equation, right, of course. So I should adjust how I ask this question. Because it becomes a lot harder if I expect you to actually expand this and turn it back into a differential equation rather than the auxiliary equation. So I really should say, give an example of an auxiliary equation that would be associated with this solution. Because, well, of course, equals 0, so that it's actually an equation. But that's all that I would expect anybody to write. And so I should rephrase this the way that I'm asking for the differential equation. This was definitely expected to be a much more difficult problem than any of them that are strictly listed in your book. But it's an interesting problem to think about. An interesting way to approach it. And it helps sort of, I guess, remember these x's and x squareds out front with repeated roots and understand the significance of those, I suppose. So, all right. Any other questions?
No, thank you.
Yeah.
Yep.
Absolutely.
Thanks.
Cool. See you then.
Have a great
Bye.
weekend. Bye.
Yeah, you too. See ya.